Hello Internet, my name is Quinn and this is Blondihacks. See, the other day I got a message from David over at Dragonfly Engineering and he said, "Hey Quinn, I wonder if I can send you something." So he did. Let's see what it is.
Hi Quinn, it's Dave from Dragonfly Engineering on YouTube. I was wondering if you could help machine a couple of new robot end effectors. Orange here, she's got the original end effector that I made when I first got her. And it's just a cube of metal without even a standoff, and it's gotten beat up and it doesn't have magnetic kinematic release plates, so she can kind of jam herself up. So we can look at some of the up-close problems of the current old end effector, which is a universal mounting cube with a bunch of different hole patterns on it that I machined like, I don't know, 7 years ago. But so here's the general mounting patterns. But what happens is, since I don't have an extension on the end of that cube from the end of the robot, when I rotate the axis or when it's traveling, the corner of the cube can actually hit the wrist of the robot, and you can see some damaged chipped paint and stuff where that has happened. The other thing I'd like to do is mount all these grippers and end effector tools on a breakaway magnet base from Thor Labs. That way, if the robot crashes into something, then this gripper will just break off from the magnet mount instead of crashing in and jamming up and getting stuck. So I was wondering if you could make a new one, or let's see if Orange wants one. Do you want one? All right. Well, it looks like you've got a customer here. And it also looks like Blue wants one as well. This is the kinematic magnet mount that I was talking about, and Blue's is a little funky too. So maybe you can make one for Blue as well. They'd appreciate it. All right. Well, I look forward to seeing what you come up with. So thanks a lot.
Let's do an extra good job on these parts, because I have a feeling you don't want to see Orange and Blue when they get angry. So here's one of those Thor Labs mounting plates that David was talking about there. And these things are really cool. They have these powerful neodymium magnets in them, and then they have these cylinders here that are ground that rest against the spherical magnets. And so there's two in one orientation, one in the other orientation. And so in addition to being a quick release and a safety mechanism, these guys are also self-aligning and very, very repeatable. It's a pretty cool mechanism. Here's the first part that we'll be making, and those magnetic blocks attached to this guy. It's basically a fancy cube with some fancy holes drilled in it for various purposes, mounting different types of end effectors on the robot. And you may notice that the drawing is in metric because, well, it's 2020. So buckle up, friends. We're going metric. Yay! Here's what we're going to use to make this cube. It's 3x3 inch aluminum extrusion. And so we're going to mark out our piece there. And the horizontal bandsaw will make quick work of cutting this guy to length. I'm leaving about 100 thou extra there on the length to allow me to square things up. And a little WD-40 to ease the process here. This saw cuts very square, so I only need to leave myself between 50 and 100 thousandths to machine away. And Yahtzee! Now, one interesting aspect of this job is that the nominal outer dimensions of this cube are 76.2 millimeters, which is 3 inches, and that's already the OD of the extrusion. So it isn't actually possible to square up this stock and stay within the tolerance on that dimension, but I double checked with the customer and this is going to be fine. So I'm just going to try to take off as little as possible. And to do that, I put an indicator on the top surface here and mapped out the surface to see what the lowest spot is, so I can try to take the absolute minimum cut on each side. Now, the other interesting aspect of this compared to squaring up normal stock is that this is a hollow extrusion, and we want the wall thickness to end up within a tolerance on all four sides. So in addition to machining as little as possible off of each side, I also need to have each side come out the same thickness within a tolerance of, let's say, a couple of thousandths. So that's an extra little wrinkle here. I'm using my 2-inch 10-flute shell mill to do this facing. I had originally wanted to fly cut this for best possible finish and to make it one nice clean pass, but if you watched my video on mill alignment, then you know that I was having some trouble with my fly cutter, so I opted to go back to the shell mill, which I know I can have success with. Sometimes it's best to go back to what you know is reliable when, the clock is ticking. And the other thing of note here is that instead of using the traditional parallel on one side and round bar or ball bearing on the other side to eliminate the influence of jaw lift on an unmachined surface, you'll note that I'm actually just using a piece of paper in there. I found that when using a piece of round bar like I normally would against the movable jaw, it was actually causing a very strange out of squaring effect on the part. The part was leaning 15 thou backwards in the vise when clamped with the traditional setup. I did a whole video about figuring all of this out, but suffice it to say for this video that this piece of paper on the movable jaw was enough and the parts came out very square doing it this way. So with those four sides squared up and to the same thickness all the way around on that extrusion, we can now switch out to a 1/2 inch end mill, and I'm going to use a small end mill to face off the ends of the part, the open square ends of the extrusion. And you could of course just do this the same way with the shell mill, but I'm not sure why I did it this way. I just thought it would be fun, I guess. And I'm setting it up on the fixed jaw with a parallel laying flat, just to have a little bit of space there in case that bottom angle is a little bit greater than 90 degrees. But I know that cut is very square, so I'm not very worried about it. And I want to keep the part as low down in the vise as possible for the most possible grip with the jaws to make sure that part stays square. And then I'm getting it roughly squared up vertically with a Starrett precision square. I tap that guy in, and then I want these parts to be very, very square. So I'm also putting an indicator on there and just running that up and down, and I tapped it in a little bit to get those sides nice and vertical. And after a couple of minutes of fiddling, we're within 1/10 of vertical over 3 inches, which I'm very happy about. And now we can start milling around the outside. So I started by trying to eyeball what the high spot is. It seemed to be this back corner, so I started there with a light pass and worked my way all the way around. And then once I had a cleanup pass all the way around, then I know I can flip it over and bring it down to dimension. We've got about 50 thou here to play with, so plenty of room to clean this guy up, do a nice finishing pass, and then flip it over. Okay, that's looking very, very nice. So we can prepare to flip this guy over now. We're going to have to deburr it, of course, so that it'll sit flat on that side. And because it's a hollow extrusion, we have twice as many edges to deburr. And then we put that machined side down, and I'm not using the parallel or the paper or any other methods now because 5 of the sides of this cube are now machined square and shouldn't need anything like that. And I'm just sanity checking everything with the square. If you watched my mill alignment video, you know at this point I'm not trusting anything on the setup of this unusual part. Now I'm going to be using the depth micrometer here, and if you've never seen this process, I thought I'd show it to you. This is how you change the range of it. You can pull out one of the bars, so it's 0 to 1 normally, and you can put in a 1 to 2 inch or a 3 to 4 inch, etc. Different lengths of bar give you different ranges of measurement on this tool. So you just pull one bar out, slide the new one in, and then the end cap screws back on. It's a very quick process. Just make sure to keep all the bars clean and so on so you don't get chips inside the mic. And I'm using the depth mic to check the length of the part in this dimension because I know that the part is, again, machined on the 3 sides touching the vise and it's seated firmly down, so this is a valid way to check the length of the part without having to disrupt my setup. And so then I just work my way around once again cleaning things up and then bringing it down to final dimension. Now we can start adding features to our part. We've got features on all 4 of the solid sides. So I'm going to set up any old side to be our top. And I'm also going to set up an end stop here. Because the part is a cube, it means I can index this cube around and add features to all the different faces and not have to re-indicate and reset up my 0 on every single operation. And as it happens, I haven't mentioned this yet, I need 2 of these cubes, so it's also going to save me a lot of setup time on the second cube. Going back to our drawing here for a second, you'll notice that all the features are referenced from a datum in the center. And you can see that the center point of the face has a tolerance marked on it, and then all features are referenced from that point. That's actually a really great way to design your own parts using a single origin in the center. So I can easily set up the part with an edge finding on both sides and using the half trick on the DRO, find that origin in the middle, and now it's very easy to navigate in the 4 quadrants of our Cartesian plane on the top surface of this part and add features as we go. And it's doubly useful on a part like this where the center axis of it is what's important. That's going to be aligned with a joint on the robot arm, and you want the attachments that are attached to this cube to be moving relative to that center axis. And so by referencing all the features from that center axis, we push all of the error that we might have with edge finding and so forth to the outsides of the part where it won't matter, and then everything in the center and referenced from that center will be precisely located. And now that we have our origin, I'm going to put a little center mark here that we're not going to use yet, but it'll be helpful if we need to change our setup or move the part for any reason to have a reference that we can go back to. So we're going to start by making this bolt circle here around the large hole in the center. I'm going to do the bolt circle first so that there's lots of material there to support all of the drilling that we're going to be doing. And to do this, I'm going to use the bolt circle function on my DRO. There's lots of different ways to make bolt circles, but if you have a DRO, this is a very easy way to do it. So it's done with this button here, which is either bolt circles or possibly something to do with navigating ships, or when frozen, it might move the island. I'm not sure. But I know when you push it, it asks for the PCD, which is the coordinate plane that you want your bolt circle to be in, and we want the XY plane. And then it asks for the center position where you want your bolt circle to be, and we want it to be at the origin. I'm just going to re-enter these numbers just so you can see the exercise here, but if the number you want is already there, you don't have to do this step. We hit enter on each parameter, and then we hit the up arrow to go to the next question. In this case, it wants diameter, so we choose 31.5 millimeters, which is the diameter of our bolt circle. And then it asks for the starting angle, which you can pretty much always put 0 for this. And then it asks for the ending angle, which is an interesting parameter. If you remember from your high school math, this is a counterclockwise angle. So it's the angle between your first hole and your last hole going counterclockwise. An easy way to calculate this is to just take the angle between any 2 of your holes and subtract that from 360, and that's going to be the angle of your final hole. And then it asks us how many holes we want, and we want 8, so we push that. And now it's telling us the 2 coordinates of the first hole, hole number 1. So all we do is we move the slides to zero out those numbers. And you can see here that we are the radius of our bolt circle to the right of our origin, and you can see that the other holes will be wrapping around the origin as we go. And the first time you use this feature on your DRO, it's a really good idea to do a dry run and just move through the holes following the DRO without actually drilling anything to make sure it's ending up where you expect. So after we're done the first hole, then we push the up arrow to get to the next hole, and it gives us 2 more numbers. So now, once again, we move the slides to zero out those numbers. And you can see that we're now lined up for the second hole, which is in this case 45 degrees counterclockwise of the first hole. And then we just proceed with that sequence, center drilling each of the 8 holes, pressing the up arrow after we're done each one, and zeroing out the axes as we go. And there's our last hole right there. Looking good so far. So we've got all of our holes center drilled. You can see the bolt pattern emerging there. And now when you get to the end, you push up arrow and you get an over sign. Game over, man. And the cool thing is, if you push up arrow again, it goes back to hole number 1. And so now we can iterate through our holes again with the next tool. So in this case, we're going to drill, and you might ream or you might countersink. So there's a good chance you're going to want to go around your bolt circle a bunch of times. And so the DRO makes it very easy to do that as well. So you don't have to change tools 4 times between every hole. Now in my case, we want to eventually ream these holes to 5 millimeters, so I'm drilling them all out to 4.5 millimeter, half a millimeter under the final size, and then we will dimension them out with a 5 millimeter reamer. And speaking of that reamer, the 5 millimeter reamer that I have is too long to go in my Jacob's chuck and still fit within the Z space that I have here on this little mill, so I'm switching to a 5 millimeter collet. And I'm going to hold the reamer in that. This is a nice way to hold reamers anyway, because it gives you that extra precision. And then we're just going to go in and ream each of the 8 holes. And I'm going a little slower spindle speed. I was drilling about 800 RPM, and I'm reaming these guys about 500, and clearing chips much more often with the reamer, because these are straight fluted reamers. They don't have the ability to clear their own chips, so you want to do lots and lots of up and down motion, clearing the chips as you go. Okay, our bolt circle's looking good. Now we're going to work on that large center hole, and we're going to need to bore this guy eventually, but I want to do most of the heavy lifting with drills. So we're going to drill it out in a few stages and get as large as we can. Drills are vastly more efficient than other types of hole making operations, so you want to get as close to your final dimension as you can with drills. So I started with 1/4 inch, and then I'm going up to 3/8 and then a 1/2 inch. And then I dug through my drawers and I found a 47/64, which is the largest drill I could find that was not larger than the final hole that I need. And this is a pretty big drill for this little mill, but it managed it just fine. And then to bring this hole to final dimension, we're going to use the boring head. Now, I have previously described boring heads as though someone described a lathe to an alien over the phone, and then the alien went off and tried to make that machine, and I stand by that description. It takes all the best parts of the lathe, it spins them around in the mill for some reason. So this guy holds boring bars, and then it has a dovetail of its own on it with a precision adjustment here that allows us to offset that boring bar from the spindle such that when it spins it will create a hole. So it's a single point cutter that you can mount in your mill. So we start by touching this guy off just like you would on the lathe. You can just turn it by hand to tell when it's touched off. And then we pull it up out of the hole, dial in some depth of cut, and then work our way down. The boring head on the mill is used for the same reasons that you would do a boring operation on the lathe, which is that when you need a very precise hole, single point cutting is the way to go. And also if you need a hole of an unusual size, or in this case, if I need a hole that is larger than the largest drill I have, or in this case, largest reamer, because we want a precision hole here. So you'd have to dimension that with a reamer. But even the best reamers, boring bar is still going to do a better job. Okay, we should be getting close here. So I'm going to go in there with my telescoping bore gauges. And space is awfully tight here, so it's a little tricky to get a good angle to use this guy, but I do manage to get in there. The head on the mill is all the way up, and I've still got just enough room to work in here with the boring head and this 3-inch part sitting on the vise. Yeah, Z space is always at a premium on any mill, but especially on these small mills for hobbyists. And we've got a little ways to go, so I'll dial in some more depth here and do one more pass, and then I think we'll be ready for the finishing pass. And here you can see the technique I'm using to feed with the boring head. I am feeding with the fine feed on the quill and using kind of a two-handed technique like you would with the compound on your lathe. I find that works better on this mill than trying to feed down with the column on a boring head. And this should be our finishing pass, so we'll check that guy. And we need 6.5 thou, so here's a way to get a precise advance on this guy is just put an indicator on it and adjust it using the indicator. And you can see here that we're 6 ticks and halfway between 2 ticks more or less, but the little scale on the boring head's not precise enough to really get down into the tenths, so you can just put an indicator on there and get your job done. Now when it's time to pull this guy out, you back it away from the cut just like you would a boring bar on the lathe, pull it out. We'll do a final check on our dimension. We're aiming for 22.49 millimeters, which is 885 thousandths, and we landed on 884 and 5/10. So we're going to take that because we're within the tolerance there on the drawing. The drawing calls for a generous chamfer on this hole, so I'm going to use what's sometimes called a zero flute chamfering tool. This is a very cool type of tool that instead of using a traditional flute to cut, it has kind of a circular hole through the middle that has sharp edges on it. And the advantage of this guy is that the tool pressure is very, very low, so it's basically guaranteed not to chatter. The disadvantage of it is that spherical opening has a very limited cutting range, and so you need a whole bunch of sizes of this tool for different sizes of holes. That's looking good, so now we can flip this guy over and add our features to the other side. The other side is quite similar. There's a fairly large hole in the middle and a bolt circle around it, in this case a simple 4-hole pattern. Now I'm going to use the bolt circle calculator again for this 4-hole pattern, but the pattern is axis aligned, so there's really no need. I mean, it's just plus or minus the same 2 values on X and Y, but sometimes I use this bolt circle tool anyway, just because it helps me prevent mistakes and keeps me from losing track of where I am on my operations. These holes are going to be threaded M61, so I'm drilling them out 5 millimeter, and then I'm going to come around with the bolt circle tool again at the end and just use it to guide my tap follower to tap the holes. And there's another hole pattern around the outside for tiny little 3mm dowel pins, and so these guys are drilled and reamed. And what's interesting about this is that 2 of the holes are blind and 2 of them are through. They all can be through, but because the holes are right at the edge on the front and back, they line up with the vertical part of the extrusion. So it wasn't specified on the drawing, but what I opted to do here is make them the same depth as the thickness of the extrusion, so that if the pin was inserted the same depth on all 4 holes, they would line up in the same place. Sometimes you have to make a little judgment call like this when dimension isn't specified on the drawing, so I just try to think about how the part might be used and do what's best for that. And to drill out the center hole, I'm once again working my way up with drills, and I'm showing you this angle because I don't think I mentioned earlier that these larger drills are all being held in collets and not in a Jacob's chuck. The reason being that on my small little mill, there isn't enough vertical real estate for a tall part like this and a Jacob's chuck and large drills. So if you're new to machining, it might seem unusual to see a drill being held in anything other than a Jacob's chuck. And so I wanted to show you this just so that you know that drills are just a cutting tool like any other, and you can hold them in lots of different ways, including collets. Now the downside to this is that drills come in many, many sizes, and so you can only use drills that you have a collet that's the right size for. And that's where Jacob's chucks really shine, because they can hold a round thing of any size. So if you can limit yourself to collet-sized drills, you can hold your drills in a collet and get a lot more vertical real estate on a small mill. And then you saw me cruise through boring out the hole and chamfering as well, just like we did before. And I'm also drilling and tapping a 9-hole pattern on the other 2 sides of the cube. I won't show that in a lot of detail because it's a very straightforward set of operations. Okay, now we have lots of deburring to do. So for the tops of the holes, it's pretty easy. I'm using a small Noga tool here to deburr these guys. And then a slightly larger one for the larger holes. And this is all great. Job done, right? Looking good? Oh my goodness. Yeah, look at that mess in there. How are we going to deburr all of that stuff? I can't get in there with a traditional Noga tool. So I've got some really trick deburring tools that I'm going to show you here for this job. The first is this guy. It's a deburring blade with a sharp angle on it, so you can get into the back of a large hole or an inside edge like that, and that works great. Now that blade, however, is too big to go through all these small holes that we have to deburr. So here's what I'm going to use for that. This is a really trick tool from Noga for deburring the insides of holes. It's a small 2-fluted deburring blade, and the blade flips around, and there's a button on the end of the tool that you can push to collapse the blade, if you will, into a vertical position. So what this allows you to do is collapse the blade, insert the tool through the hole, and then expand the blade behind the hole, pull upwards, and do your deburring. And then when you're done, you can collapse the blade again and pull it back out of the hole. And these little tools only work on a very narrow range of hole sizes, so there's 3 different sizes of this tool that you can buy, and I'll link to these guys in the show notes below. And the little blades on them are also replaceable. But this is a very slick little tool. You can see what a nice job it does, and for a deburring job like this, this might be just about the only way to do it. And after a lot of quality time with the deburring tools, our cube is looking mighty fine. So I think we are just about done with this portion. And now let's grab that magnetic base again and just see how that might interface together. So it's got an alignment pin on one end that looks like it goes into various holes that we've produced here. And you can see that the threaded hole in the center lines up with the threaded holes on our cube. And it looks like this plate can be mounted in various orientations all around this cube. So once again, I'm not sure exactly how this thing is going to be used, but you can see that it's got a lot of flexibility. And oh, did I mention we need 2 of these? Yeah, I made 2 of them. So plenty of work was done here, but there's more parts to be made for this project. We'll get to those next time. Thank you very much for watching. Please do consider supporting me on Patreon. Patreons are the only things keeping the lights on here. I don't have corporate sponsors. Thank you very much for watching, and we'll see you next time.